Hi everyone, I'm Michele Scarlato. I'm presenting the OSS open source software license compliance within the FASTEN project, and I'm working in this project with the Endocode. So the content of this presentation will be what open source software is and how it's influencing nowadays the software industry, the concept of package management in open source software, the concept of dependency networks, what OSS license compliance is, and issues related to the OSS distribution. This before to enter into details of what FASTEN project is and what are the main goals. Trying to describe, to give an overview of the overall architecture and going into details on how we are performing license detection and compliance within FASTEN. So open source software allows code reutilization, simultaneously reducing development and maintenance costs. And these softwares are hosted principally in repositories such as GitHub, GitLab, or Bitbucket, and forges such as Maven, PyPy, or Debian repository, for example. The development and utilization of open source software, driven by its collaborative nature, is giving life to software ecosystems that are worldwide populated, and generally ruled by package management systems that are used to provide version consistencies during package installation or removal, deciding which version is chosen for each library. An example here is the simple logging factory for Java, and its dependency log4j. And on the left, we can see how the pom.xml is representing this dependency, and how, in turn, this dependency has its own dependencies. This approach is creating, generating complex graphs. Package dependencies networks are in fact composed by packages and their dependencies, and the versioning of both are increasing the network size and complexity, generating complex graph that is the result of this process. So what OSS license compliance is? OS license compliance try to answer the question like, how do I know that I'm not violating anyone's copyrights or copyleft, that I'm not linking against code featuring incompatibility licenses? Taken from the research community literature, we can start to have a view of, for example, Professor Diomedes Spinellis explain that an accurate selection of open source components imply considering licensing issues, narrowing down your search, examining whether the project's license is compatible with your business model, mission, or other software that you are using. And meanwhile, Philip Ombredan, which is the author, the creator and main contributor and maintainer of ScanCode, which is a tool that we are also using inside of our license detection tool, presents in his recent paper a study on license documentation, where the study shows that fewer than 5% of approximately 5,000 popular free and open source packages contain complete and unambiguous license documentation. This means that still developers are not providing clear information regarding licenses, and this is the real issue that we are facing now from our perspective, because it's not easy to retrieve this information precisely. So other issues related to the OSS distribution are that package maintainer offer often their source code for free, and this impact on code modification because deprecating and adding features cannot be easily accessed. Furthermore, small and large companies are using many OSS packages, and they do not pay maintainers to do that. to maintain their packages, so their dependencies. So why and what would motivate this maintainer to keep their code updated? And other issues related, for example, to the license compliance is how instances of code distributed without permission can be spotted. And a few incidents, like the LeftPad and Equifax ones, have shown that removing one library from an ecosystem or not caring about vulnerabilities on a specific package version could bring down a considerable network of sites, like in the case of LeftPad, which has been removed from the npm ecosystem, or generate a huge money loss, like in the case of Equifax, where the security team didn't took into consideration seriously, or couldn't take into consideration a vulnerability that generate a huge loss of money. So what FASTEN project is a project founded by the European Union within the Horizon 2020 umbrella, composed by a consortium of university and companies, such as the Athens University, the University of Technology of Delft, the University of Milan, and companies like Endocode, Software Improvement Group, SIG, XWIKI, and OWT, which is a consortium of companies that are using open source software. So what FASTEN means, FASTEN is an acronym of fine-grained analysis of software ecosystem as a network, and as main goal to support the DevOps teams and help developers tracking, managing, and mastering dependencies. So within the main goals, we have to increase the software ecosystem robustness by making package management more intelligent, by creating an ecosystem-wide, fine-grained core graph at the functional level. This would provide a fully precise usage analysis and an impact analysis. So we would be able to answer to questions like, does this vulnerability affect my code? Am I linking to strict permission licenses like GPL code? Or if I modify this code, how many clients will I break changing the code? Or how can I safely update my package with a new release of library of dependency? And here we can have an overview of what the knowledge base architecture of FASTEN is. So we have a layer stratification where we have input from forges such as the above mentioned Maven, PyPy, or Debian repositories, and other input from security repositories like CVE, security issues repository, security vulnerabilities like CVE and NFD. We have a processing layer built upon a Kubernetes cluster where we find where our plugins are executed, and messaging within them is ruled by Kafka. Then we have a storage composed by a metadata database, RocksDB graph database, file system, and the graph that we are generating, the dependency graph. Then we have an output that can be provided with through raw data or provided to analyzer that are performing risk or licensing assessment, and these results can be provided through test API. And finally, this output can be interfaced to a website or to continuous integration tools like Travis, Jenkins, or GitHub Actions, for example. The Dataflow is going in this direction. Usually, we analyze in the specific case of Maven architecture, which is the one that we are carrying out now. We analyze the POM file, we clone a repository, and we start to store information in our metadata database. Meanwhile, there is a job synchronization performed through Kafka message that should be carried on by each plugin before to consume his own message. It means that every plugin is receiving a message from Kafka, and that is the moment where the plugin starts. As we can see, our plugin is going to start after the vulnerability assessment. And these results, as said before, could be provided by REST API or integrated in a website or in tool like continuous integration tool. How our plugin is functioning? Well, after the cloning, we receive a Kafka message at start, trigger our license detection phase. These licenses are inserted into the knowledge base, so we scan for licenses in the final package, in the final binary that has been created, and these licenses are then retrieved by another process called license compliance verifier, which is verifying that these licenses are compatible with the outbound license. And soon we will explain what this terminology means. This plugin is composed by two subphases that both are ruled by Kafka message. And we can, dividing the license detection from the license verification part, we can start to understand that there is a phase where licenses are detected and categorized, because we have to keep in mind that when we do license compliance, we need to provide a set of inbound licenses that should be matched against the outbound license, which is the one declared within a package. So the output of this phase is to the increasing of the FASTEN knowledge base with the detected licenses, and separating the inbound licenses for a given package with the outbound license. And the validation part is made against checking against a compatibility matrix if the set of inbound license has compatibility issues with the outbound ones. So this phase is made in this way. An array of license is parsed. So for every element of the array is performed a check, gathering the information, the compatibility information, compatibility rules from the compatibility matrix, and that are stored in Boolean values, and creating an array of Booleans. If all the values are true, means that there are no compatibility issues, the assessment is flagged as valid. If is just one of these Boolean is false, the assessment will be flagged as false, providing an output. To go in deep in what really is doing license compliance, I need to show you this simple graph, which is representing just a subset of the whole license OSI approved. And we can see that we have 4 layers. One is a permissive license, another one is the weakly protective license, and then we have the strongly one and the network protective license. What is important to understand from this example of graph is that there are licenses that have unidirectional compatibility. For example, just to cite one compatibility that we can find in the permissive layer, MIT could be used within a package released under Apache license. It means that if I am importing dependencies that have as outbound license, so as declared license MIT, in a package that I want to release as Apache 2.0, I can do that. The point is that probably I'm releasing that package under Apache 2.0 license because I have some dependencies that are Apache 2.0. So combining these 2 different inbound licenses, I can provide as outbound license just the less permissive one. And this rule is applied to all the logic that we are observing here, where the arrow are indicating the direction in which the license can be assumed valid. For example, if we go in the strongly protective layer, we can see that GPL 2.0 can be compatible with GPL 3.0, but is not reverse. So if I'm taking in input GPL 3.0 dependencies and GPL 2.0 dependencies, I cannot release under a GPL 2.0 outbound license. I should use GPL 3.0. So this was important to just explain to you which logic is adopting the license compliance verifier. And here there are some screenshot and example of input and output, trying also to explain what so far we did with the LCV part that need to be integrated in the FASTEN architecture, but has been developed providing API endpoints. So the logic is that it will be running in the architecture as a Docker container and just responding to get and post, mostly post, made by a Java code insert of the Maven architecture. Here is an example of the execution of the Flask implementation, which is one of the implementation that we realized upon the LCV libraries that we build during this project. And for example, the second screenshot is related to an endpoint that is collecting most of the endpoints that we are using within the Flask implementation. As we can observe, for example, there is one endpoint that is to retrieve GitHub API's outbound license. So providing a GitHub URL, a GitHub API URL, we are able to extract the outbound license parsing a JSON. The compatibility verifier, simple verifier is related to the scan code output, scan code ID for specific licenses, for inbound licenses, using the an SPDX ID for the outbound one, because we opt to use SPDX IDs mainly. So most of the time, when we find an ID that is not in SPDX format, we have a function that modify that map the ID from scan code, for example, to the SPDX one. And of course, we are providing this kind of interface also for debugging purpose, but also to provide the final user eventually with some tool that can be used as a in a web interface fashion, as a web graphical user interface. But mainly, we are going to use inside of FASTEN architecture just the version with the through post HTTP post. For example, here is an example of how graphically is functioning our tool. If we are going to insert using the compatibility SPDX flag API endpoint, if we are going to insert that we have as inbound license Apache 2.0 and MIT, and as outbound license we have MIT, the compatibility flag will be false, because as we said before, this kind of association would require having Apache 2, which is the less permissive one, as outbound license. And this is the logic is we created this kind of this structure of endpoint because whenever the assessment is true, we don't need to provide logs, or at least it's a passage that we can avoid, because we already detected that all the licenses are compatible, because the final goal is to provide an assessment that is really a flag. But in the case of a negative flag, it's important to provide the final user or final developer with a correct output. So we are also running another endpoint. We are also running another post towards another endpoint that is providing us with the correct output. In this case, for example, it's clear that Apache 2.0 is the one that is creating troubles because it's not compatible with the MIT as an outbound license. And this is an example of how we thought to integrate this LCV Python logic inside of Maven FASTEN deployment. Practically would be using API calls, API method through Java code. This whole LCV license compliance verifier logic is also working in pipeline, in continuous integration and continuous deployment pipeline, both with GitHub Actions and Jenkins. And it's probably important to mention that we test our endpoint with the Postman. To do that, we are using Newman, which is a module for a node package manager, a node module. And I will link I'll link a video to this presentation that you can take a look into if you want to see the full process of pipeline. As a reference, I mentioned Ombredan and Professor Spinelli's, and here I put the reference of the two papers that I mentioned during the presentation. And I have to say that it's been really clarifying having read the paper on this topic. Mainly, I understood that it's possible to augment further the precision in license detection by not only performing scanning, and this was very well explained in the Ombredan paper, free and open source software license compliance tools for software composition analysis, because so far we just scan the compiled project to find the license inside of that project, but it's possible to perform matching techniques, because meanwhile there is an ecosystem of database that are indexing piece of that indexing code used within packages. So it's possible to match against this database portion of code during the license detection phase, because sometimes it's possible that the developer are using piece of code without maybe declaring where they took it from, and this is a way to help the detection phase to understand under which license a portion of code has been already released, because the portion of code is already out there. So it's very interesting to have the possibility to go further in this process and provide a more accurate license detection in order to help the community to develop their software under license that doesn't have issues within each other. So I hope to be thank you for the attention, and I hope to have been clear enough explaining this giving to you this short presentation, and I would be very happy to try to answer to your question. So far, thank you.